Hello, good morning, students. We are continuing our topic alcohols, phenols, and ethers. Today, we are going to see about the structures of functional groups present in alcohols, phenols, and ethers. Let us see the structures of functional group in alcohol. See here CH3OH. Now in this alcohols, the OH group is attached to carbon by sigma bond formed by overlap of sp3 hybridized orbital of carbon with a sp3 hybridized orbital of oxygen. So here this OH this OH group is bonded with this carbon. So this is sigma bond, and this sigma bond is formed by overlap of sp3 hybridized oxygen and sp3 hybridized carbon. So in these two sp3 hybridized atoms, the overlapping take place, axial overlapping take place, and this sigma bond formation take place. This COH bond angle in alcohols is slightly less than tetrahedral bond angle. So tetrahedral bond angle is 109 degrees and 28 minutes that we have studied in 11th standard. Tetrahedral bond angle is 109 degrees and 28 minutes. But here this COH bond angle is less than the expected tetrahedral bond angle 109 degrees and 28 minutes, that is 108 degrees and 9 minutes. So this is due to repulsion between lone pair of electrons of oxygen. Now here these two lone pair of oxygens present here, these are two lone pairs of electrons present on this oxygen. So they repel each other, and because of their repulsion the bond angle is get distorted, is get reduced than the expected tetrahedral bond angle 109 degrees and 28 minutes. Okay, so there is repulsion, lone pair repulsion is greater, and hence this bond angle is get distorted. Okay, now see the functional group in phenols. This is phenol, benzene ring, and OH. In phenols, the OH group is attached to sp2 hybridized carbon of an aromatic ring. The CO carbon oxygen bond length is 136 picometer. This bond length is 136 picometer. Here, this OH group in phenol is bonded with this sp2 hybridized carbon. Here, this carbon is sp2 hybridized carbon. Okay. So, this bond length 136 picometer in phenol is slightly less than that of in methanol. This is due to first, partial double bond character of unshared electron pair of oxygen with the aromatic ring. See here, double bond, single bond, and this oxygen contains lone pair of electron. So this is, so these are in conjugation, double, single, and this double bond, two lone pair of electrons. So there is conjugation. And second point, the sp2 hybridized state of carbon to which this oxygen is attached. So, so the bond length in this phenol, CO bond length in phenol is less than that of alcohol. So in alcohol, that bond length is 142 picometer, because this carbon is sp3 hybridized carbon. There is no double bond with which this electron pair on oxygen may be in conjugation, but here there is no double bond and carbon is sp3 hybridized carbon. So here the bond length is shorter. Okay, now let us see about the structure of functional group in ethers. So the example is taken methoxymethane, CH3O, CH3. See, the bond angle is 111.7 degrees, and the bond length between C and O is 141 picometer. See, in ethers, four electron pairs, that is two bond pairs and two lone pairs. So here this two bond pairs, first and second, first and second. So these are two bond pairs, and this first and this is second, two lone pairs. They are arranged approximately in tetrahedral arrangement. So when this formation take place, so this is having tetrahedral geometry. They having tetrahedral geometry or tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral bond angle. It is due to repulsive interaction between these two bulky alkyl groups. So here this alkyl groups, methyl, and this is second methyl, there is repulsion between these two alkyl groups. So though here the arrangement is tetrahedrally arranged, but because of repulsion between these bulky alkyl groups, two methyl groups, they repel to each other and the bond angle increases. Actually, tetrahedral bond angle is 109 degrees and 28 minutes. But here repulsion take place between these alkyl groups. So these bonds get repelled, push away from each other, and the bond angle increases. It is 111.7 degrees. Okay. The carbon oxygen bond length is 141 picometer, is almost the same as in alcohols. In alcohols, the bond length was or bond length is 142 picometer. Okay. So this is about the structures of functional group in alcohols, in phenols, and in ethers. Okay. Now let us see the preparation of alcohols from alkenes. First, by acid catalyze hydration, alkene reacts with water in presence of acid as catalyst to form alcohols. In case of unsymmetrical alkene, the addition reaction take place according to Markovnikov's rule. So here alkene has carbon-carbon double bond plus the addendum. The reagent is water, H plus OH minus. H plus OH minus. H2 means H plus OH minus. In presence of any mineral acid. In presence of acid as catalyst. So water reacts in this way. If the alkene is symmetrical, one hydrogen goes to this carbon and OH goes to another carbon, double bond changes to single bond, and we get this alcohol. We get this alcohol. But if alkene is unsymmetrical, this is propene, CH3 CH double bond CH2 plus water in presence of H plus in presence of acid catalyst. What will happen? H plus and OH minus. The negative part of reagent goes to that carbon of the double bond which carries least number of hydrogen. So here across this double bond, this carbon carries one hydrogen and this carbon carries two hydrogens. So the negative part of reagent will add according to anti-Markovnikov's rule. Sorry, according to Markovnikov's rule. Okay. So OH will go here and H plus will go here, double bond changes to single bond. So isopropyl alcohol will form. Okay, this is first method of preparation. Next, by hydroboration oxidation. By hydroboration oxidation. Diborane BH3 twice or B2H6 BH3 twice, or it is also B2H6. It reacts with alkenes to give first trialkene borane. First, it gives trialkyl borane as the addition product, and this trialkyl borane is oxidized to alcohol by hydrogen peroxide in presence of aqueous NaOH. So this is alkene. This is alkene plus BH3 twice. Here BH3 twice H plus BH2 minus. So here CH3 CH H CH2 BH2 plus second molecule of alkene. It gives the next product dialkyl borane. Again it reacts with third molecule of alkene, that is propene, and it gives trialkyl borane. So first the addition product trialkyl borane is obtained. Now this trialkyl borane is oxidized using hydrogen peroxide in presence of sodium hydroxide. It gives alcohol, propan 1-ol. It gives propan 1-ol. So this is formation of alcohol by hydroboration oxidation method. By using alkene and diborane. So first, remember again, first trialkyl borane formation take place. First, trialkyl borane formation take place. This trialkyl borane undergo oxidation with hydrogen peroxide in presence of sodium hydroxide. It gives alcohol. And BOH thrice, hydroxide of boron. Now next preparation method is from carbonyl compounds. From carbonyl compounds. By reduction of aldehydes and ketones. Aldehydes and ketones having carbonyl group CHO and here C double bond O. Aldehydes and ketones are reduced to corresponding alcohols by addition of hydrogen in presence of catalyst, catalytic hydrogenation. The usual catalyst is finely divided metal such as platinum, palladium or nickel. Catalytic hydrogenation means, so this catalyst like as platinum metal, palladium metal or nickel, or it is also prepared by treating aldehydes and ketones with sodium borohydride NaBH4 or lithium aluminum hydride LiAlH4. Okay, aldehydes yield primary alcohols while ketone gives secondary alcohols. See here, in this reduction of carbonyl compound, there are different reducing agents. One is catalytic hydrogenation, means hydrogen reacts in presence of catalyst like platinum, palladium or nickel. Okay, or by using reducing agent sodium borohydride NaBH4, or by using reducing agent lithium aluminum hydride LiAlH4. Okay, so these are different reducing agents. Here in this example we had taken both examples, catalytic hydrogenation or by using this sodium hydroboride, sodium borohydride as reducing agent. So what is said here, aldehyde gives primary alcohol, means aldehydes on reduction gives primary alcohols while ketone gives secondary alcohol. So let us write the general reaction RCHO. Reduction, on reduction it gives, this is reduction, so it is difficult to write by this pointer pen, so it gives RCH2 OH. OH. Okay, means aldehydes on reduction gives primary alcohols and ketones they gives, let me write here, ketones on reduction gives secondary alcohol. So this is very easy to me to write in this way. Secondary alcohol. Okay. So remember this, aldehydes on reduction gives primary alcohols and ketone on reduction gives secondary alcohol. See here, this is the example of aldehyde RCHO plus catalytic hydrogenation. It gives RCH2OH. This is primary alcohol and RCOR dash ketone. On this reducing agent, it gives this secondary alcohol. Okay, so aldehyde and ketones both are carbonyl compounds. C double bond O H and C double bond O R, both having carbonyl compounds. They can be reduced by using catalytic hydrogenation in presence of catalysts like platinum, palladium, or nickel as catalyst, or by using reducing agents NaBH4 or lithium aluminum hydride, whatever it may be. But aldehydes on reduction gives primary alcohols and ketones on reduction gives secondary alcohols. Okay, let us go ahead. Reduction of carboxylic acids and esters. Carboxylic acids are reduced to primary alcohols in excellent yield by lithium aluminum hydride, which is a strong reducing agent. Okay, see carboxylic acid RCOOH in presence of LaH or lithium aluminum hydride. They gives alcohol RCH2OH. But what happens here? This lithium aluminum hydride is very expensive reagent, and hence it is used for preparation of special chemicals. Okay, so commercially, if we want to prepare alcohol by using acid, carboxylic acids, so acids are reduced to alcohols by first converting into esters, and then they are reduced by using hydrogen in presence of catalyst or catalytic hydrogenation to alcohol. See, simple general reaction is given here. Carboxylic acids converted into esters. So when carboxylic acid react with alcohol in presence of dehydrating agent acid, it gives corresponding ester. So here H and OH, water molecule is lost and corresponding ester formation take place. This ester, this ester is undergo catalytic hydrogenation H2 in presence of nickel, platinum, palladium. Okay, it gives it gives primary alcohol RCH2OH. So carboxylic acid to ester and ester on reduction it gives alcohol. Okay. Now next method from Grignard reagents. From Grignard reagents. Alcohols are produced by action of Grignard reagent with aldehydes and ketones. So here just carbonyl group is shown because aldehydes and ketones both having carbonyl group. How this basic action take place? It is given here. Carbonyl group from aldehyde or ketone plus RMGX Grignard reagent. General Grignard reagent is given. Alkyl magnesium halide. Okay. So here this R attacks on this carbonyl carbon and this bond of oxygen goes to magnesium and it gives the complex adduct or complex compound formation take place. So this alkyl group comes from Grignard reagent. So RCOMgX. This complex compound, this complex compound or unstable compound is further reacts with water. It gives alcohol plus MgOHX. MgOHX. How this reaction take place? See, when this adduct is hydrolyzed, HOH, it reacts with water or undergo hydrolysis and in this way reaction take place. RCOH, this is alcohol, plus MgXOH, this is MgXOH. So in this way alcohol formation take place. So this carbonyl carbon is from aldehyde or ketone. Okay. Now here the overall reaction, the overall reaction using different aldehydes and ketones can be given as. Now here see, formaldehyde is used. What will happen when we use formaldehyde or methanol? So methanol plus Grignard reagent. This alkyl group attacks on carbonyl carbon. So it gives RCH2OMgX. This is complex or adduct. This complex further hydrolyze, it gives RCH2OH, which is primary alcohol, which is primary alcohol plus MgOHX. Okay. If we take any aldehyde other than formaldehyde, any aldehyde other than formaldehyde and reacts with Grignard reagent, reacts with this Grignard reagent RMgX. So already this aldehyde is having alkyl group. R is present there in this aldehyde and this R dash comes from Grignard reagent. So R and this is R dash which is from Grignard reagent. Okay. So the alcohol obtained is secondary alcohol. This is secondary alcohol. And now see the third example of ketone, RC double bond O R. When this ketone reacts with R dash MgX, that is Grignard reagent. So it has alkyl group R dash. Then the adduct formation take place which contains these two alkyl groups already present in ketone, and this R dash comes from Grignard reagent. So this carbon is bonded with three alkyl groups, and this COMgX, which on further hydrolysis it gives OH, that is alcohol formation take place. So this OH is bonded to this carbon, which is bonded to another three carbon atoms. So this is tertiary alcohol. It is tertiary alcohol. Okay. So in short, when formaldehyde or methanol reacts with Grignard reagent, when formaldehyde or methanol reacts with Grignard reagent, it gives the intermediate or complex compound or unstable compound, which on further hydrolysis it gives primary alcohol. Any aldehyde other than formaldehyde when reacts with Grignard reagent, it gives complex compound or adduct or unstable compound, which on hydrolysis it gives secondary alcohol, and ketones on reaction with Grignard reagent it gives tertiary alcohols. See, in this formaldehyde or methanol, carbonyl carbon has no alkyl group. So this alkyl group attach, which is from Grignard reagent. Okay, so only one alkyl group is present on carbon, which is directly bonded to OH. Here what happens? Already this aldehyde is having its own alkyl group, and when it reacts with Grignard reagent, the new alkyl group, that is R dash, comes. This R and R dash both bonded to carbon, so OH bonded to this carbon, which is having which is bonded with two different carbons, so it is secondary alcohol. And about this ketone, already ketone is having two alkyl groups, and the new alkyl group comes from Grignard reagent, so it gives tertiary alcohols. Okay, so here remember this point. The reaction produces primary alcohol with methanol, secondary alcohol with other aldehyde, and tertiary alcohols with ketones. Okay, now preparation of phenols. Preparation of phenols. So first, phenols can be prepared by using chlorobenzene, and this process is Dow's process. Dow process. Chlorobenzene is first fused with sodium hydroxide at very high temperature and pressure, 623 Kelvin temperature and 150 atmospheric pressure, followed by the treatment with dilute HCl to obtain phenol. See, this chlorobenzene reacts with sodium hydroxide at high temperature and high pressure. It gives first sodium phenoxide, ONA. ONA means NaOH. This hydrogen of NaOH is removed by this benzene ring, phenyl ring. So it becomes sodium phenoxide. This sodium phenoxide, on further treatment with dilute HCl, it gives phenol. It gives phenol. So this process is known as Dow process. Chlorobenzene with sodium hydroxide at high temperature and pressure, It first gives sodium phenoxide, which on treatment with dilute HCl, it gives phenol. Okay. Now next is by using cumin. By using cumin, this is commercial method of preparation of phenol. Cumin is nothing but it is isopropyl benzene. So this cumin on their on air oxidation in presence of isopropyl benzene on air oxidation in presence of cobalt naphthenate. It gives cumin hydroperoxide first, which on decomposition with dilute acid, it gives phenol with acetone as valuable product. So this is CH3CH3, and to this second carbon benzene ring is attached. So this is isopropyl benzene, or its common name is cumin. So cumin, when air oxidized, react with oxygen in presence of air with cobalt naphthenate at very high temperature, it gives cumin hydroperoxide. It gives cumin hydroperoxide. That is, these two oxygen atoms get add between this CH bond. See, these two oxygen are added here in this CH bond. Okay, so this is cumin hydroperoxide. This cumin hydroperoxide further on heating with dilute acid, what happens? See, the decomposition take place in this way. That is CH3C. 1 minute. Let me show you this reaction again. This OH attack on this carbon, and this bond goes here. In this way, decomposition take place. So this carbon detached from this benzene ring, and this carbon double bond oxygen, that is acetone formation take place, and phenol is obtained. Got it? Now next method, from benzene sulfonic acid. Benzene sulfonic acid on neutralization by NaOH, it gives sodium benzene sulfonate, which on fusion with solid NaOH at high temperature, it gives sodium phenoxide followed by reaction with dilute acid gives phenol. So this is benzene sulfonic acid. Benzene sulfonic acid. Benzene ring bonded with SO3H. So first neutralization take place. benzene sulfonic acid plus sodium hydroxide. It gives sodium benzene sulfonate, SO3 minus Na plus. Okay, this is sodium benzene sulfonate. Salt formation take place. This sodium benzene sulfonate on further fused with sodium hydroxide at very high temperature, that is 523 Kelvin, it gives sodium phenoxide, which on further reaction with dilute acid it gives phenol. Okay, remember again, benzene sulfonic acid is neutralized by using sodium hydroxide. It gives sodium benzene sulfonate as salt. This salt further fused with sodium hydroxide at 523 Kelvin, it gives sodium phenoxide. This sodium phenoxide on treatment with dilute acid, it gives phenol. From aniline. Aniline is treated with nitrous acid. So nitrous acid is prepared in situ, that is by reaction of NaNO2, sodium nitrite and HCl. It gives HNO2 at low temperature to obtain benzene diazonium chloride. This benzene diazonium chloride on hydrolysis, it gives phenol. See this reaction, aniline. This aniline is treated with NaNO2 plus HCl. This NaNO2 and HCl, they reacts with each other to form HNO2, nitrous acid, and it gives benzene diazonium chloride, N2 plus Cl minus, which on hydrolysis it gives phenol with liberation of nitrogen. Okay, this is fourth method for preparation of phenol. The physical properties of alcohols and phenols. First, boiling point. First point, see, with increase in number of carbon atoms, van der Waals forces increases, which in turn increases the boiling point of alcohols and phenols. If alcohols and phenols, if they having more number of carbon atom, then their van der Waals forces between intermolecular, they increases, and hence as the van der Waals force of attraction increases, the boiling point of that alcohol or phenol also increases. Okay, that is methyl alcohol, ethyl alcohol, propyl alcohol, as alkyl group goes on increasing, means number of carbon atom goes on increasing, the boiling point also goes on increasing. So what is given in this point, less is the number of carbon atoms in alcohol or phenols, their boiling point is less. As alkyl group or number of carbon atom increases, boiling point also increases. Why? Because of van der Waals forces increases. Second point, with increase of branching in carbon chain, the van der Waals forces decreases with decrease in surface area and hence decrease in boiling point. decrease in boiling point. So branching means if there is branch side chain present, then it reduces the surface area, it decreases the surface area, and surface area decreases, the van der Waals forces of attraction also becomes weak. As van der Waals forces of attraction become weak, the boiling point also becomes less. Okay, so here branching decreases the boiling point. What is given in this second point? Branching decreases the boiling point. Third point, the high boiling points of alcohols and phenols is mainly because of the presence of intermolecular hydrogen bonding in them, which is not present in ether and hydrocarbon. The OH group in alcohol and phenols involved in intermolecular hydrogen bonding as follows. How this OH is responsible to form intermolecular hydrogen bonding in alcohols and phenols, it is given. Hmm? So in this way it is given. See, ROH, this is first molecule. ROH, second molecule. This is third molecule and this is fourth molecule. So see this dotted line. So as OH is polar bond, oxygen is more electronegative, so it has partial negative charge and hydrogen has partial positive charge because the electron pair is more attracted towards oxygen. So partial negative charge and partial positive charge. Here partial negative and partial positive. So partial positive charge of second molecule, that is hydrogen, is bonded or form a strong hydrogen bonding with oxygen of the first alcohol molecule. So this is hydrogen bonding. Here also hydrogen bonding and here also hydrogen bonding. So number of alcohol molecules are associated through this strong hydrogen bonding and hence their boiling point is strong or boiling point is higher, because to break this force of attraction, strong force of attraction, rather strong hydrogen bond, more energy will required and hence alcohol having higher boiling points. Same way, see, in this case of phenols, OH, this is second molecule of phenol, this is third molecule of phenol, and they form intermolecular hydrogen bonding. Here same example is given. So because of this strong hydrogen bonding, the boiling points of alcohols and phenols is higher. Intermolecular hydrogen bonding in alcohols and phenols. Physical state. See, this is the picture of intermolecular hydrogen bonding in alcohols and phenols. Now, physical state. Lower alcohols are colorless, toxic liquid, and having characteristic alcoholic odor. Pure phenol is colorless, toxic, low melting solid, having characteristic phenolic odor. Now about solubility. Solubility of alcohols and phenols in water is because of their ability to form hydrogen bonds with water molecules. With increase in size of alkyl or aryl group, the solubility of alcohols and phenols decreases. See here example of methyl alcohol is given, CH3OH. when this methyl alcohol dissolved in water, H2O. This is first water molecule shown, this is second water molecule, and this is third water molecule. So here, because of polar nature of this OH bond, here also polar nature of two OH bonds of water. So here these all dotted lines are nothing but hydrogen bonding between water and alcohol molecule. So here H plus partial positive charge and partial negative charge of oxygen, partial positive charge of alcohol and partial negative charge of water, partial positive and partial negative of water here also and here also. In this way, because of this hydrogen bonding, alcohol is soluble in water. But as this alkyl group goes on increasing, size of alkyl group goes on increasing, the solubility decreases, because here carbon and hydrogen, these are non-polar bonds. These are non-polar bonds. So this is the reason behind the solubility of alcohols and phenols. Alcohols and phenols are more soluble in water than other organic compounds. See here one or two questions. Let us see. So here two examples are given and we are asked to write the order of boiling point in increasing order. Their boiling point with increasing order. So pentan 1 all, butan 1 all, butan 2 all, ethanol, propanol, propan 1 all and methanol. So here methanol 1 carbon, so it is having very less boiling point than ethanol. In this way, let us see what is the answer. Methanol, ethanol, propan 1 all, butan 2 all, butan 1 all, here branching, butan 2 all means branching. So here 1 carbon, here 2 carbons, here 3 carbons, butan 2 all, 4 carbons, but and here also 4 carbons, but here at second carbon the OH group is present as a branch. Branching decreases the van der Waals force of attraction, so it has less boiling point than butan 1 all, and the next higher boiling point of pentan 1 all because 5 carbons. Okay, the next example, alcohol, butane, alkane, aldehyde and ether. So here N-butane, because no polarity, no hydrogen bonding, ethoxyethane, less polarity. Here pentanal, here also more polarity than ether, and here pentan 1 all, so here also hydrogen bonding, and here the reason is strong hydrogen bonding, so boiling point of pentan 1 all is very high in this all organic compounds. So this order is in increasing order, increasing their boiling points. Okay, About these chemical reactions, we will see in next lecture. Okay, so listen this lecture again one time, read textbook and try to solve different examples. Okay, let us stop here. Thank you.